Hello folks. Well, this time around I want to talk about Valgrind instead of GDB as a debugging tool. This one's a little different. It's not interactive. It's going to basically run in the background as we run our program, and it's going to produce some information about the execution of the program for us afterwards, more or less. So we'll take a look at how this works. We are going to look at Valgrind as a profiling tool later, but it is really useful for some debugging information, especially for memory issues. So the idea is Valgrind is just like GDB. To be able to analyze our program, it needs the program to be compiled with the -g flag. So you go through, recompile your program with -g as an option, and then we'll actually execute our program through Valgrind. So we'll run Valgrind. I'm going to stick it in verbose mode so it says a lot about what's going on, and then whatever the name of your program happens to be, run. So it's going to run your program normally, but it's executing with Valgrind. Now, if you've got command line arguments, you can throw those on as well. So, / your program 10 foo whatever, and it will go through. Your program runs normally. Valgrind will produce some output before the program runs. It might produce some output during the execution, and it'll produce a summary at the end talking about any potential problems it's spotted. So it will happily run through, blather away. It can produce information about things like unreachable code, uninitialized variables. So there's all sorts of bits and pieces it can give you information about. And then we can also use it to detect memory leaks. So it can give us a much better analysis of where we might have forgotten to free up memory as we were going through. If we're using mallocs and delete, or mallocs and freeze, or if we're using new and delete, or whatever it might be, then Valgrind actually sticks in code with every malloc to figure out, here's space that was allocated, I'll keep track of it, and then later on checks to see if you actually deallocated that space and if you still have pointers to it. So really useful for leak checking. So to do that, we have to give Valgrind some extra options saying I want you to actually do that. So it's Valgrind, I'm going to use the -v again, and then that doesn't show up well on the slide. That is actually 2 dashes. So --leak -check equals full. So that's saying do full leak checking. And again, the name of your program and whatever options it's going to take. And at the end, it'll spew out a summary of what's going on in it. And that summary will actually be broken down, and it'll tell you things that are definitely lost. So essentially this amounts to cases where it's absolutely sure that you allocated the space and then you lost the pointer to it. So it is pretty definitely a leak. And then indirectly lost are cases where you do things like you've got a tree of nodes, and you allocate the top node, then you allocate the children, and the top node's got pointers to the children, etc., etc., etc. And you do something like delete the top node before you delete the interior nodes, the child nodes. And so it's got no way to get at those, and so it will tell you that that stuff is also lost, but you've got this kind of indirect loss taking place. So it gives you a bit of a breakdown of what's going on. We'll take a look at some examples in just a second, just briefly, so you can see it in action. When you're going through and doing this, the full leak checking can produce a lot of information if you've got a fairly complex program. So I would suggest going through and making sure you do your basic debugging first. So just run it to get rid of the basic errors. And then you can turn on leak checking at different levels of information. So maybe run it in just the basic version first, so just leak check is yes. And then once you get those taken care of, you can do the full analysis if you want to with the leak check is full. So just as a point of advice for at least minimizing the amount of debugging clutter you've got in the output from Valgrind, that might be the way to go. All right, I wanted to actually show this in action just briefly. So we're going to look at our real simple program where I've got some memory allocation and deallocation in it. What did I call this? Leaky. So really straightforward. We've got a function that dynamically allocates an array of however many ints you ask for. We're going to have one function here that calls that, assigns it to a pointer, a local variable, and then just ends. So what that means is that for sure since we only have that pointer inside our bad pointer function here, we're never going to be able to get at that space again. So it's been allocated and can never be deallocated. For sure, that's a lost space. We've got one in here where we'll just allocate the space, and then if the allocation succeeds, we'll delete it. So hopefully this doesn't reflect a leak. So I think ints are 4 bytes on our system, so that first one has got 40 bytes that's definitely lost. This one we're creating 6 ints, so we've got 24 bytes that's created and deleted, hopefully. And then a little further down at the bottom of our main routine, well, in our main we call those 2 functions, and then we allocate an array of 9 characters and don't delete it. The reason I've got string copy in here is I want to talk about what Valgrind tells us about the memory in just a second here. So we've got some examples of it working and or successful deallocation and unsuccessful deallocation. Let's see, we wanted to compile this. I suppose I should throw in my error checks, and let's call the executable leaky. Hopefully that's about right. So we compile it, and then we want to run Valgrind, and I'm going to stick it in verbose mode. I'm going to say I want to do full leak checking, and I just want to run my leaky executable. That sounds about right. So we get this big blob of information going on where it's going to go through and gives us this huge massive information about what's taking place. So let's try that with just leak check equals yes, and you'll see we get a little bit less going on there. Actually, that didn't look like that much less. However, okay, let's go through and we'll pipe this through less so we can actually look at this stuff as it's coming out. Whoa. What have I done here? Ah. Keep trying. Let's see if we can stick this in a file and see if I can see what I've got taking place here. Ah, it's writing to standard out or standard error, not to standard out. That's what's going on here. Let's try something like that. That's what's going on. Okay, so now let's take a look at blah and we can see what kind of information it's giving us. So let's see. It goes through, does the usual spew about what's taking place. It essentially walks through the code telling us what's going on. A lot of stuff that we're not really interested in here. Do we have a summary at the bottom that I'll skip to for a second? Yeah, so we've got a summary down here telling us that we've got those 9 bytes from that string at the very end that are definitely lost. It's got the 40 bytes from that array that we allocated in bad pointer dev, and again it points out that that's definitely lost, and we get this definitely lost summary, 49 bytes lost in these 2 different blocks. So we get summaries of the errors that it manages to discover. Right? We can see that it was searching for pointers to those 2 not free blocks. And so it goes through and tries to give you information about what's taking place. Now, it also goes through and gives you a lot of information about what's taking place in the various library routines that are handling the various allocations and deallocations, which is probably stuff that you're not horribly interested in, but go through and have an explore and see what might be interesting there. Again, you can start using this as a tool to give you extra information about your debugging process. But again, that summary at the end is probably the most useful place to begin. Right? You get an idea of what functions are involved in whatever it is you're doing. Right? We've got create is actually doing the allocate. Well, new is doing the actual allocation. create is calling it, that's coming from bad pointer, and that's the one that's the source of our problem here. So definitely interesting and useful information. All right, I will leave that there for now. The joys of Valgrind.